Process engineers spend their days mapping out fluid systems, but eventually those abstract calculations must be translated into physical steel, brass, and concrete. This document is a technical specification sheet, the primary translation device between theoretical design and physical installation. Specifically, we are analyzing the blueprint for a flanged end gate valve built to the PN10 pressure class. To understand the performance of this valve, we have to parse three distinct domains: its structural geometry, material chemistry, and operational limits. Mastering this document allows an engineer to predict exactly how the hardware will behave under the stress of a live 10-bar industrial fluid system. The first domain requires translating the two-dimensional schematic into mechanical movement. This drawing details the valve's internal actuation mechanism. Part 9, the solid wedge, descends to create a physical barrier across the pipe to stop flow. Connected to it is Part 3, the stem. This valve features a non-rising stem configuration. In a standard valve, turning the hand wheel pulls the stem and the wheel upward. In this non-rising design, the stem rotates in a fixed position, and the internal wedge threads up the stationary stem like a nut on a bolt. This kinematic choice eliminates the need for any vertical clearance above the valve. In a densely packed facility where overhead space is restricted by existing infrastructure, a standard valve would be impossible to actuate. The two-dimensional drawing dictates the spatial and architectural constraints of the entire piping facility. Why not manufacture the entire valve out of a single block of standard steel? This parts list maps compromises, balancing structural integrity against internal friction. Part 10, the body, is gunmetal, bronze or nickel aluminum bronze, providing containment and corrosion resistance. Internally, moving parts need different properties. The stem is brass. When two identical metals grind against each other under high pressure, they can experience galling, a form of destructive friction where surfaces essentially cold weld together. Pairing a softer brass stem with a bronze body prevents this. The dissimilar metals glide smoothly, ensuring the valve won't seize up after years of inactivity. The final material vulnerability is the gap where the rotating stem exits the pressurized body, requiring Part 6, the gland packing. The specification calls for PTFE, or Teflon. This chemically inert, low-friction polymer is the only material capable of sealing the rotating shaft without restricting movement. The body material dictates environmental survival, but internal material compatibility dictates the actual lifespan of the valve. The final phase of decoding defines the absolute operational limits and standards for the hardware. The hydrostatic testing parameters in this box dictate the safety margins required before the valve is cleared for use. Note the discrepancy in the data. The body is tested to 15 kilograms per square centimeter, while the seat is only tested to 11. Engineers test the outer shell to a higher burst limit to prevent external leaks, while the internal seat is tested only to the limits of the PN10 operating pressure. This bottom table details dimensional geometry, ensuring modularity. Dimension A, the face-to-face measurement, is standardized so engineers can replace failing valves without redesigning pipe layouts. A small tolerance note reveals these dimensions allow up to a 5 mm variance. A 5 mm tolerance is a massive variable when welding rigid infrastructure, proving that even standardized components require field adjustments. These tables represent the final contract between the manufacturer and the engineer, guaranteeing both safety margins and system-wide compatibility. Decoding a technical document involves tying these three distinct domains back together. The schematic dictates the spatial kinematics of the non-rising stem. The parts list maps the chemical and frictional survival provided by the brass and PTFE, and the data tables guarantee the modularity and safety margins of the testing differential. Those theoretical numbers finally manifest as a physical, robust industrial component, installed on the line and actively fighting against immense fluid pressure. The specification sheet maps the exact mechanical reality of industrial flow control.